Hi, let's take a look at the new Micsig MDP series high voltage differential probe. Now, this is the new MDP series is the replacement for the DP series, which we've seen in many previous videos. In fact, Micsig actually developed this DP700 variant of their DP line of high voltage probes at my request, because I was looking at selling this. So they actually designed this to actually meet, try and meet the same specs as my HVP70 probe, which I still sell on EEVblog.store down below. An excellent probe made by Sapphire, by the way. So they did this version with the ×10 and ×100 ranges to match this, because their normal one, including this new one, is ×20, ×200. So the new MDP series doesn't have this ×10, ×100, but they developed this for me, and then I tested it, and I'll link in the videos if you haven't seen it, where it wasn't that great. It didn't meet its spec on the common mode rejection ratio, the CMRR. And I've done an excellent video, by the way, even if I do toot my own horn, on what is common mode rejection ratio and how to measure it. So I'll link in that video down below if you haven't seen it. And I've done a full teardown and reverse engineering video of this design as well. So anyway, I didn't end up selling this, but Micsig did actually sell it. So quite a few people bought it, but they actually also confirmed my tests that didn't quite meet the common mode rejection ratio. So Micsig have developed this new MDP series, which actually replaces it. Look at that. Get the accessories. They're the same as the ones that came with the DP series, and it does look very different. So we're going to take a look at this, and we're going to measure its common mode rejection ratio and compare it with the other probes. But if you want a more in-depth video, go and watch the previous ones on the DP700 for the common mode rejection. So anyway, it comes in a sexy carry case here, and it does look like a high quality bit of kit. And of course you get the crocodile clips with it, and you also get the big long easy hooks like this as well, the big grabbers. But yeah, this actually looks and feels a lot better than the existing design, the plastic housing like this. It's much smaller, but it's a dual head approach. So it's got the high voltage differential part down here, and then differential amplifier, and then a driver in here, which drives to a receiver down here, and then that drives your scope direct. And it's got the fancy stuff like 5 megahertz bandwidth limit. So this has a little micro in it, and ADC and DAC and whatnot, and you can actually zero out the offset on this. Very handy. So nice little die-cast alloy case, as is the head as well. So it's a better design than the previous one. And it's got the shorter cables like this, because I know that a lot of people don't like the integrated probes like this. They prefer the shorter ones. I know a lot of people would have preferred to see just the banana jack straight in here, and then they could make their own probes and little shorter ones, so you can get higher bandwidth, less inductance, and less interference and stuff. But yeah, at least they've done these short, as opposed to the much longer one on the previous one. So yeah, this is a more betterer design. And this new design is actually a spin-off from their cutting-edge SIG Offit optical fiber probe technology. Hence, it looks very similar to the optical fiber probe. Look, there's the two heads. It's much shorter, but obviously, they've got a similar sort of microcontroller in there with the offset stuff and things like that. So yeah, it's spin-off technology from that. And I don't want to toot my own horn, but I have done an excellent video on showing you, demonstrating the practicality and use of these high voltage optical fiber probes. I'll link that one in as well. It's an awesome video. As you can see, they do offer this in the one we've got, 20 times and 200 times switchable, 50 and 500 and 100 and 1000. Sadly, they don't offer my preferred one, which is the 10 times. And interestingly, the output voltage is only plus minus 3 volts now, as opposed to 7 volts that we got on the previous models. So we'll see what that's like in terms of noise floor. But anyway, they boasted to me in an email that, yeah, I will be happy with the common mode rejection ratio of this thing. All right, for testing this, we're going to get out the big gun, the Rohde & Schwarz MX04 scope, like we used in the previous common mode rejection ratio video, and it's got a USB-C input. Nice. They do provide a very long lead here for connecting to your scope, but you could connect it to any other power source as well. Would have been nice to have a little shorty, I guess, but your mileage may vary. Now, if we compare the MDP series to the old DP series, the DP series, of course, had my one, the times 10 times 100 version, but then it jumped up to times 50 times 500, whereas this is available in times 20 times 200. Now, noise figures here, the 10007 had less than 15 millivolts RMS there, and 40 millivolts for the times 50. And if we go over here, they actually specify it for the 5 megahertz bandwidth and the full bandwidth. They're both 100 megahertz full bandwidth, and it's a little bit worse over here, 45 millivolts, and a bit worse over here on the times 20 at 22 millivolts as opposed to the 15 over here. So we'll measure that, but yeah, it's not as good. Now, the common mode rejection ratio here, they are specified at different frequencies. A DC, of course, greater than minus 80 dB here, and that's exactly the same here. 100 kilohertz looks to be the same at 60 here. Well, they've got minus 60 here. They put 60 here, but I explained in my previous video why they have minus 60 and some have 60 because they're just lazy and leave it off. But the old one only specified 1 megahertz here, and for the 10007, it's greater than minus 45 dB here. Whereas the new series, they don't give you the 1 megahertz figure. They jump up to 10 megahertz and give you minus 30, which is worse, of course, than minus 45. It's 15 dB worse at a lot. And that could be fine if they actually gave you the 1 megahertz figure, but they don't. So, yeah, we're just going to have to measure this thing. And as I said, the output voltage are 7 volts for the previous one, and the new one's plus minus 3. But technically, that's neither here nor there, as long as your scope is capable of actually measuring down that low and going into the noise floor as well. So, yeah. Let's check it out. But the difference in the attenuation here, times 10 to times 20, hasn't impacted the maximum differential voltage, which is DC plus peak AC. Still 700 volts on the either the times 200 or the times 100 range with the old model. So it's still more than capable, of course, of doing like your general purpose mains power supply stuff. No worries whatsoever. So what we're going to do is zero this, so we need to short the input out. You can't do that unless you've got a banana to banana, so you can put it on the current range of your meter, no worries. So we've shorted out our input here, and then we press our 0 button here, and boop, you hear 1 beep, it's fine. If you hear 3 beeps, then it's failed for some reason. And by the way, this thing does have, they do recommend a 10-minute warm-up period for this. So just be aware of that. You can't just necessarily slap it on and start your measurement if you're doing anything accurate. So I've left it for about 5 minutes, and you can see it's probably a little bit below the center line there. So I'm going to actually zero that again, and it did its beep, and see, it's actually gone up, and now it's, you know, the center of that noise is now in the center. I know it wasn't much, but it'll depend on the ambient temperature, how long you've had it powered up, blah, blah, blah. But just be aware, of course, that you have to set your scope up to times 20 probes. So if your scope doesn't have to have that, then you'll have to do the multiplication manually, I'm afraid. And we use the standard 1 mega ohm input termination. You don't need 50 ohm termination for this. You don't want that. So just, yeah, standard scope input. As a baseline, I think I've been left that for half an hour. I had to do something else. I can probably tell by the time up there in the edit. And it shifted. What, 20 half a division, 20 millivolts, maybe, on average. So, just a bit of a baseline. But yeah, these things do drift because they have active amplifiers in there. So, yeah, just be aware of that. It's why it has a 0 function. Alright, please excuse the crudity of the model. Didn't have time to build it to scale or to paint it. I'm using the same GAN MOSFET driver that I used in my SIG off-it video. So if you want a very extensive technical video about how fast GAN transistors work and high voltage probing and all that sort of stuff, then check out that video. But I've got all 3 probes hooked up. I've got the new MDP700 on channel 2, DP10007 on channel 3, and the HVP70, which is only 70 megahertz bandwidth, on channel 4 here. Now, because the MDP700 is actually shorter leads here, they do actually include some extended leads here. So I've put those in, so it's not twisted as much here, but it's basically the same length as the other two probes here. So I'm probing the switching output of this MOSFET here, and you can see that the green trace here, which is the new MDP one, it is substantially larger than the other two. The ringing on there is substantially larger. That's the effective inductance of the lead. So yeah, let me try and untangle it and see if we can get better. So I've got the really short probes on there. You can see the difference that makes. So, well, let me switch over to the green here, and you can see that, yeah, the ringing is shorter on that. But anyway, this isn't an extensive test. This is just a sanity test to show you that all three probes basically are performing the same at 1 megahertz switching frequency here, and all the ringing all has to do with the probing. But I've gone through that in the previous video. So I don't know, just wanted to have a play around with their simple sanity check just to make sure they're on par. But yep, they basically are. So you can see in there all three channels like that are all performing identically. They all do the same high frequency stuff. So there you go, we can switch through those, and yeah, pretty groovy, no worries. And all three of them having a 70 volt differential voltage. I've currently got it to 65 volts. That's on the lowest range anyway. So I'm going to turn that up and turn the up, and the Micsig there started to flishy flash, showing you that it's over range. The other ones don't actually have that. So, but let's keep turning it up and see which one craps out first. Come on, we're 79 volts, 80 volts. And yeah, it's definitely the DP10007, which is the orange one there. That's just, yep, it's died. It's died. So the others actually still have an ability to keep going above that. And you can see that it's clipped there at 91 volts. And the others start to, yeah, do silly buggers as well. So slightly better. The others are slightly better than the old DP10007, but that's neither here nor there. That's just for funsies. All right, so we've got the remote oscilloscope interface here. I've got the input to the MDP700 shorted on full 100 megahertz bandwidth on channel 2 here. And you can see that little sigma signal there. That is AC RMS. Basically, I've done a full video on that. Again, very interesting and informative video. What haven't I done? And we're talking mean of 13 millivolts RMS noise here. And that's on the times 20 range, and the spec is less than 22 millivolts. So yeah, easily meets that. No worries. But you've got to remember this new probe is available in 100 megahertz, which is what we've got here, and the MDP701, which is 150 megahertz, and the 702, which is 200 megahertz. So, but they don't break down the specification for that. So maybe their noise figure is like on the highest 200 megahertz one. I don't know why you wouldn't break it down per model, but anyway, there it is. And I switched on 5 megahertz bandwidth here, and you can see it's dropped, but I'll just clear the statistics there. And the sigma that we're looking at, because you don't want RMS, because RMS includes any DC offset. That's why you want AC RMS, which is the standard deviation, which is that sigma function there. And we're talking 5.4, and the spec is 8 millivolts. So, yeah, meets it. And now on the times 200 range, remember you've got to change your attenuation down here. So I have actually changed that, so we can go in there and have a look to verify that I've actually done that. Go into probe, and you can see I've got 200 on there. So our figures are correct. And so let's clear that, and we get 40.5 millivolts. The spec is 80. No worries. And I've changed it to 5 megahertz bandwidth, and let's redo that. Should only be a smidgen smaller. We're talking 31 now millivolts. But once again, the spec is 70. So yeah, it's ballsing it in. Now we've got the old model DP10007 in times 10 mode, spec of 15 millivolts RMS noise. So I'll just clear that, reset the statistics, and we're talking 12.7 there. Yep, meets it. So they're basically on par with the new model. So yeah, it's neither here nor there. And we don't have a 5 megahertz bandwidth limit on the old model. So yeah, I'm just not going to bother, cobbling together some external bandwidth limit thing. Doesn't matter. And times 100 mode, reset that. We're looking at 23.6 millivolts. So the previous model was almost half the noise on the higher attenuation setting than this new model. So that's not terrific. And the EEVblog HVP70 on times 10 mode. Let's give that a reset. And we're talking 10.4 millivolts. So that's the clear winner. And on times 100 mode, let's reset it, 37 millivolts. So that is less than the new MDP70, but higher than the DP700. And again, we don't have a 5 megahertz bandwidth hardware limit on that, so we're not going to test it. All right, please excuse the crudity of the model. Didn't have time to build it to scale or to paint it. I've shown the setup and gone through all sorts of stuff in the previous CMRR video. I'll just quickly, briefly cover it here. We've got a signal generator output here, which we can go up to 100 megahertz. And then we got that going into a 50 ohm terminator here, so we don't get any transmission line issues. And then, I've got just a banana breakout here so that we can connect both of the inputs, short them out. Yes, we're actually shorting the inputs out to the positive output of the signal generator here, so that we're effectively putting a common mode signal on both of these wires here, shorted together, but so it's common mode signal relative to ground over here, and that's the whole point. Now, I'm not sure with the times 200 range of this new MDP700, I'm not sure how we're going to go with signal level, because I can only get 5 volts maximum on our SIG-Gen. We'll give it a go, but I'm not hopeful. It was already borderline with the times 100 on here. So then you just have the output of the SIG-Gen. In this case, we'll do the DP700 first, just to get a baseline, and then the output of that is just going into channel 4, and then we're going to use the frequency response analyzer, although you don't need a frequency response analyzer to do this test. You can just do a spot frequency with an external, so you don't even need an internal SIG-Gen. You don't need a response analyzer, just do it spot frequency-wise, and I might show you that as well. So how we set this up with the frequency response analyzer, or the spot frequency, is that we're down in the very low signal level here. So I've got it on the times 200 range, which will give us the highest, the highest common mode rejection ratio, the highest signal level. Now I've got to have it in HD mode. So I've got HD mode turned on, and you can see that gives us an effective resolution of 16 bits. That's very important. Now, I discovered one thing on here is that I do have average mode turned on. And watch this. If I put 20 averages on, okay, and I've set 20 averages, so we should actually get 18 bits of resolution on this thing, and I've got the signal level set to maximum 5 volts peak to peak into a nominal 50 ohm load. I've got the start frequency 10 kilohertz, stop frequency 50 megahertz. The input is channel 1, so that's from the function gen, and the output is channel 4 here. That's the output of the probe. So I should be able to run that. Okay, but watch up here. I expect, right, average of 1. I expect an average of 20. But we don't get it. It switches to an average of 1. Now, I'm not sure why that's the case. I have to talk to Roden Schwartz about that, because I want my 20 averages, damn it. I don't care how long the frequency response. If it takes 20, if it has to take 20 samples on each one. Anyway, here we go. We're getting our response from the red as the phase. So we should expect to see a phase change up here somewhere. And then we're going up to 50 megahertz on this one. And up. And there's our phase change, and which is fine. There's nothing wrong with that. And okay, so at 10 megahertz here, you can see that it's at 19 and a half dB, which is terrible, Muriel. And by the way, we've got to get this right. The probe is set up for the times 100 ratio there. But at 1 megahertz, but we don't have a spec for the DP700. Remember, this is the older design. We're talking about minus 40.45 dB, and the spec is minus 45 dB. And this is why I went back to, when I first tested this, I went back to Micsig and I said, hey, this doesn't meet the spec. And they said, oh, okay, we'll test it. And they confirmed it didn't. And they said they'd work on it. 6 months later, oh, sorry, we're still working on it. 12 months later, oh, we're still working on it. And what, a year or two years later, bingo, we've got the new design came out. So that's the old DP10007, and it doesn't even specify at 10 megahertz. So yeah, the old one wasn't a great probe. Let me show you the HVP70. Okay, so I just connected up the HVP70 probe. It's only got 70 megahertz bandwidth, but we're only going to 50 meg anyway. And everything's the same. It's the same gain. It's on times 100, so I don't have to make any other changes. And I can just run this again, and we should see it becomes significant. It should be significantly better. So at 100 kilohertz there, we're at like minus 63 dB or something, 64 dB. So come on, you can do it. And we're going to phase change there. Like I said, phase change is not a problem. And we've got another phasey. But the problem here is that we're down in the noise. Okay, you can see the waveforms up the top. They're not that terrific. But anyway, at 10 megahertz, it's better, right? At 10 megahertz, it is minus 43. So way better. And its spec is minus 40, I think. Okay, so I've got the MDP700 in, and we'll just change that to 200. Apart from that, we can just rerun that and see what we get. Whoa, bit of a jump there, but you can see, look at the signal levels up the top. Okay, we're down in the noise. This is where the averaging would have helped, but it won't let me do the average. Oh, no, this one's got 18-bit HD now. It's switched to 16-bit. It was 18-bit down there, so I'm not sure what was going on there. That's interesting. Anyway, yeah, it's a bit higgledy-piggledy, isn't it? We don't get a smooth response, but we're down in the noise. Look at the signal level it's trying to measure down there. It's 100 millivolts, but that's gained up by 200. Okay, so it's right down in the noise. Anyway, we do have a spec of minus 30 dB at 10 megahertz, and we're getting minus 46. So it is substantially better than the spec. That's pretty good. So let's actually do this. Let's go back and just do this as a spot frequency thing. I said I'd show you that. So generator, 5 volts peak to peak on our signal generator. And let's say let's do the 10 megahertz thing again, okay? Turn our SIGGEN on. There we go. That's channel 1. Turn on channel 4. And channel 4, we're going to have to turn it right down, okay? You can see that we are down in the noise, right? We're at 500 microvolts per division, but we're only 12-bit, okay? So we need, unfortunately, it's reset all of our stuff. So we have to go back in. We have to switch HD mode on, right? Because it's just, now we're getting 16 bits, but look at that, right? There's almost, you can kind of sort of see there, it's out of phase, right? It's dipping here and it's going up there. You can almost see it, okay? So we're gonna have to turn some averages on here. We're in sample mode, so we'll turn on some averages, right? And we've only got the one average, so let's just go 20 averages, right? And we can kind of sort of get our signal level there. So you can see it's that frequency response graph is going to be very how you're doing, because we're down in the noise, okay? So that is 10 megahertz. But it's also reset our probe. So we've got to go in our user-defined probe. Set our bandwidth of our probe. Let's take that down to the 100 where it's supposed to be, okay? Maybe we'll get some, no improvement there. And manual attenuation, and of course you can set the attenuation, but it makes no difference, right? But we can actually set that to the times 200 there, but it just changes the scale. It doesn't physically change the signal level into the scope. So yeah, there you go. Yeah, try and get a signal out of that. So let's turn on our sigma or standard deviation measurement, AC, to get rid of any DC offset. So we'll add that for channel 1, and then we'll also add that for channel 4 as well. Okay, so there you go. We can get both of those, and we can turn our statistics on. Okay, and boom, we now have, right, figures that we can actually work with. So a mean here of 9.2 millivolts, okay, divided by 1.78 volts, okay? And then we get our log of that, and then we multiply that times 20, and that gives us minus 45 dB, okay? And our 10 megahertz spec is minus 30 dB. So it's ballsing it in, absolutely ballsing that in, no problems. And I can now switch it to the times 20 mode, and I'll show you that it'll just drop right off. Here we go. And times 20. There you go. It's no better. The DC offsets are changed, and I can zero offset that, of course. There you go. That was zero offsets, and right, there's just nothing there. You're just measuring unicorn farts here, pretty much. But if we go up to 100 megahertz, we find that we do actually get something, okay? So now we've actually got some signal to work with here. And it's interesting, you can see the wavering of the average there, and that's because the DC offset is drifting. We're so far down in the noise that the gentle drift in the DC offset in this thing, that's why it has a zero offset button, is causing that, and it's moving slowly because we've got 100 averages turned on now. If we turn the averages off, you'd see it go burko. If we turn average back to sample there, that's what we're dealing with. That's what we're dealing with. Now you'll notice at 100 megahertz, our signal levels actually dropped here. It's not a problem from a measurement point of view, because what we're actually measuring at that particular point of the like the channel 1 input is fine. So our measurements are correct, but our signal level has dropped because we do actually have some system capacitance there. So let me actually disconnect the cables, and you'll see the amplitude actually go up a bit. There you have it. I physically disconnected them. So that's interesting, huh? But as I said, it doesn't make a difference if the amplitude actually drops, as long as you're measuring it correctly at the channel 1 input, which we are. All right, so let's reset our stats here. And what do we got? We've got a mean of 26.2 millivolts, and divided by 804.5 millivolts. We get log of that, and we multiply that by 20, and we're getting minus 29.7, pretty close to 30. And what is our spec at 100 megahertz? Minus 26 dB. So yeah, it meets the spec. So yeah, it's a reasonably decent probe for CMRR. So there you have it. That's the MDP700 there. Street price of about 260 euros from Bartronics there. 220 US. I mean, they've got like a ticket price of $4.99 there. That's pretty pricey, but 220 bucks street price is excellent. Oh yeah, look, you can buy the MDP702. There you go. Oh, it's jumped up to 400 euros. Wow, for the 200 megahertz one. Yeah, as I said, I would not spring for the extra money for the bandwidth here, because it's all about the probing. And when you've got just the banana plug interfaces like this, you're going to struggle to get your performance with your probing at those sort of frequencies. So 100 megahertz is already more than enough. That's why my HVP70 is only 70 megahertz, because it comes with the banana plug leads. You can't get a higher frequency interface for your higher frequency interconnects. So yeah, I don't know why they bother manufacturing that, actually. Yeah, I'd just get the 100 megahertz version, or even like a 50 megahertz, or even like the old school 20 megahertz high voltage differential probes. It's still incredibly useful. So yeah, I think just stick with the 100 megahertz jobby and you'll be fine. But it does seem to meet its performance specs, so I'm reasonably pleased with that now. But yeah, they couldn't fix the DP series. They tried for like a year and they couldn't fix it. So anyway, thoughts and comments down below, and I ran out of time for the teardown. So if you want to see a teardown of this thing, maybe even another reverse engineering video, please leave it in the comments down below. But you've got to interact on the videos so I know that you like them. You've got to watch them, you've got to thumbs them up, and you've got to subscribe and all that sort of stuff, so I know I can get the metric that you enjoy this sort of stuff. So anyway, hope you enjoyed it. Catch you next time.